Okay, good morning. Happy Wednesday. Here to give you a little bit of help with Lab 3, that Mu That You Do lab that I'm asking you guys to tackle today. And so in order to help us go through this, I'm going to share my screen and just walk you through this just a little bit. So let's jump over here and let's see. So if you go over to Canvas, today's Wednesday, March 25th. We'll have office hours from 10 to 11:30. You've got answers to the little ball drop mini lab from yesterday, Tuesday, March 24th, right here. If you don't have the packet, it's lab 3 towards the back of the packet, that Mu That You Do, part 2. So you can print this out if you need it. The video that I want to show everybody is right here. And this is in case you don't want to actually find an object and give it a push, let it come to a stop. The video ends up looking a little something like this. And this is in essence all you need to do. We've done plenty of labs like this where we get something going and we allow it to come to a stop. Think about what force is causing that to come to a stop. It's the force of friction. And what we're going to do is look at this from a couple of perspectives here. And now let me switch over to my other place that I want to share with you. And let's see if the phone cooperates with me. It looks, yeah. All right, so this is the lab. And so the first thing is find an unobstructed stretch of floor space, all right? And that's what the video did. We just want to give this thing a little bit of a shove, and we're going to find the initial velocity and the acceleration of this object using kinematics. Now, important, in that video, if you choose to use my video, right? The ball rolled 3 meters in 2.5 seconds. And so you're going to want to use that as you make your table and do the kinematics and find the initial velocity and acceleration. All right. And then as we move on further down, it says determine the mass of your plastic vehicle. And if we were in the lab, we would have been doing this with some plastic carts. I'll tell you that, oh goodness, I'm going to have to check something here real quick. The mass was 0.5 kilograms for the object that I put into motion. So I had a 0.5 kilogram object. And so what we're doing in this lab is we're doing some old physics. We're doing some kinematics, we're doing some F equals ma. And then we're gonna move a little bit further down here. And we're gonna say, okay, so after we've figured out the friction force using F equals ma and drawing a good force diagram, we're gonna figure out what mu is. And remember that mu is just our ratio of the friction force to the normal force. So if you've drawn a good force diagram and you have the values that I've given you there, the 3 meters in 2.5 seconds for a 0.5 kilogram mass, that should all be pretty good review stuff. Then we head over to the second page of the lab. Excuse me. Now, this is written up using delta E, and I don't want that to confuse anybody. Just realize that delta E is change in energy. Delta means change. So if I'm talking about delta E, I'm talking about change in energy. And we said yesterday and the day before that a change in energy is simply going to be work. And so we're going to represent that as W. So don't be troubled because I've thrown in this delta E. What is that? All right, so now what we're going to do in the first page, we looked at things from the perspective of kinematics, F equals ma, and all of this sort of older physics that we've been doing for a while. And now we're going to look at this object that is literally rolling across a surface. We're going to look at it from the perspective of energy, right? It's on the ground and it is clearly moving at the beginning, and over here it is at rest. So if we think about this as the initial situation and this as the final, and we think about writing an energy expression, you should be able to think about what type or types of energy it has here at the beginning. So think about using TEI And because this thing is clearly undergoing an energy change, it's either an energy gain or an energy loss. I'll leave that to you to decide. We do want to put in a work term. And remember, we always put the plus sign, and we trust that the signs will work out. Gains tend to typically be positive values. Losses tend to typically be negative values. And then you think about what type or types of energy this thing has at the end. Again, it's sitting on the ground and it's at rest. So you'll use that type of thinking to figure out the delta E, which really, remember that delta E is just work, okay? All right, and so now we continue on down. What sign was delta E? Why does this make sense? And now for the magic, all right? You're going to take the friction force that you figured from the previous side, and you're going to put an appropriate sign in front of it, all right? Think about helping or hindering forces. Friction is most definitely one of the two of those, and we want to put a sign in front of it that's appropriate for that. We know that the distance traveled, I told you that it traveled 3 meters in 2.5 seconds. So we're going to use that information here to come up with a value. And then we've got some questions to answer here. And then the big finale, what is the formula for determining delta E, the change in energy? And remember that delta E is just work. And then what I'd really love is to see if you could figure out how to determine, sorry about that, see if you could figure out how to determine mu using energy. And the hint that I'll give you there is to go back to your expression that you wrote at the top of the page here, TEI plus W equals TEF. And now that you have from number 11 right here, come up with a formula for W for work. If you know what work is and you know what the formula is for it, see if you can take that a step further and use that to determine mu. And so you'll see the solution that I'll post tomorrow. And hopefully this little video gives you a leg up, a helping hand, whatever you want to call it, to try and make this a little bit easier for you. I'm proud of you guys that have been working really hard, and I appreciate it very much. And I look forward to catching up with some of you guys. Class time tomorrow, Thursday, March 26th is at 9 a.m. We'll record it for those of you that can't make it. Office hours, as always, are running from 10 to 11:30 each day. So drop in and say hello and ask questions if you have them. And I'll see you guys soon. All right, take care. Bye-bye.